Have you ever wondered what filled the universe before atoms existed? Before hydrogen, before helium, before any element had a name? Tonight we drift into a time so ancient that matter itself hadn't learned how to be law, a realm where the very building blocks of reality danced in forms we can barely imagine. If you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. These stories find their way to curious minds like yours, and your support helps keep the wonder alive. Picture this. For nearly 400,000 years after the Big Bang, the universe was a seething ocean of free electrons and atomic nuclei, too hot and energetic for atoms to hold together. According to data from the Planck satellite and UMAP missions, temperatures soared above 3000 Kelvin everywhere. Any attempt by protons to capture electrons was instantly shattered by the violence of photons. This was the cosmic dark age before starlight, before chemistry, before the first stable matter. Yet within this chaos, the seeds of everything you see tonight were already taking shape. Take a slow breath. You are made of atoms that once swam free in that primordial fire. Tonight we drift into a realm where existence itself defied every rule we understand, where the universe compressed into a point smaller than imagination could grasp, holding every particle that would ever form your body, every photon that would ever warm your face, every atom that would ever become a star. Picture this cosmic birth certificate written in mathematics so extreme that our finest theories crumble like ancient parchment, unable to describe what transpired when everything we know occupied zero space while containing infinite density and temperature beyond any scale physicists have devised. Take a slow breath as you consider this. General relativity, the elegant framework Einstein gifted us for understanding gravity and space-time, simply breaks down at this singular moment, while quantum mechanics, our most precise tool for describing the microscopic realm, also surrenders its predictive power when faced with conditions so extreme they transcend physical law. According to calculations from leading cosmologists at institutions like Princeton and Cambridge, this singularity represents not merely the beginning of matter or energy, but the actual birth of time itself, making any discussion of what came before as meaningless as asking what lies north of the North Pole. Within this incomprehensible point, every force that would later govern galaxies, every interaction that would bind atomic nuclei, every quantum field that would give particles their mass, existed in perfect unity, indistinguishable from one another in ways that challenge our deepest intuitions about reality. The temperature here transcends measurement because heat itself hadn't yet separated from other forms of energy, creating conditions where the distinction between matter, radiation, and space-time dissolved into pure potential waiting to unfold across cosmic time. As research from NASA's Theoretical Astrophysics Division suggests, this moment represents the ultimate mystery in physics, where our most fundamental questions about existence converge into a single blazing point of pure creation that would soon begin the most magnificent expansion story ever told, setting the stage for everything from quantum fluctuations to conscious thoughts about the cosmos itself. Imagine holding in your mind something smaller than the smallest conceivable speck, yet containing within its impossible boundaries all the hydrogen that would fuel a trillion suns, all the carbon that would form the backbone of life, all the iron that would flow through your veins at this very instant. Here, in this moment beyond moments, the concepts we rely on to make sense of reality simply vanish. There was no up or down, no left or right, no yesterday or tomorrow, only pure existence concentrated with such intensity that space and time themselves emerged from this cosmic seed, like flowers blooming from invisible soil. Modern supercomputers at facilities like CERN struggle to model even the aftermath of this primordial explosion, yet somehow this infinitesimal point contained the precise mathematical relationships that would govern everything from the spiral arms of distant galaxies to the electrical impulses firing in your neurons right now as you contemplate this magnificent mystery. What emerged from this singular instant would cascade through nearly 14 billion years of cosmic evolution, each subsequent moment flowing from this one perfect, incomprehensible beginning that remains forever beyond our complete understanding. A eternal reminder that the universe itself began as something far stranger and more wonderful than our earthbound experience could ever prepare us to imagine. As we follow that idea deeper into the cosmic dawn, we encounter the Planck Epoch, a period so brief that if you tried to count these moments, there would be more Planck times in a single second than there have been seconds since the universe began. Yet within this fleeting instant spanning only 10 to the negative 43rd seconds, reality operated under rules so alien that everything we consider fundamental about existence simply didn't apply. Close your eyes and imagine a realm where temperature soared to 10 to the second. Kelvin, a heat so intense it makes the core of our sun feel like Arctic ice, where thermal energy reached levels that would make stellar furnaces seem cold and distant, creating conditions that stretch our understanding of what hot even means. During this extraordinary epoch, the four forces that govern every interaction in our modern universe, gravity that keeps your feet planted on Earth, electromagnetism that powers the device you're listening on, the strong nuclear force binding atomic cores together, and the weak force enabling radioactive decay, all existed as one magnificent superforce, unified in ways that theoretical physicists at institutions like MIT and Stanford spend lifetimes trying to comprehend through elegant mathematical frameworks. Picture space-time itself not as the smooth cosmic stage we experience today, but as a seething quantum foam, a bubbling froth, where the very fabric of reality fluctuated wildly at scales smaller than anything we can measure, where geometry itself writhed and twisted in patterns that would make the most complex mathematical equations look simple by comparison. Here, in this primordial theatre, matter and energy hadn't yet learned to be distinct entities, existing instead as pure quantum potential, neither wave nor particle, but something far more fundamental that contained within itself every possibility for what the cosmos could become. Research from leading quantum gravity theorists suggests that during this phase, space-time experienced fluctuations so violent that virtual particles popped in and out of existence faster than light could cross the distance of a proton, creating a cosmic dance of creation and annihilation that somehow held within its chaotic choreography the seeds of order that would eventually crystallize into galaxies, planets, and the consciousness contemplating these mysteries right now. The entire observable universe, everything from the most distant quasar to the atoms in your fingertips, occupied a region smaller than the tiniest subatomic particle, compressed into a space so minute that comparing it to anything in our experience becomes meaningless. Yet somehow this impossibly small realm contained all the information needed to unfold into the vast cosmic web we see today. According to calculations performed by researchers at places like the Perimeter Institute in Cambridge, quantum gravity dominated every aspect of reality during this phase, making space-time itself subject to the uncertainty principle, causing the very coordinates of position and momentum to blur together in ways that challenge our deepest assumptions about the nature of existence. What fascinates cosmologists most profoundly is how this epoch of pure chaos somehow contained within its quantum fluctuations the precise mathematical relationships that would later manifest as the elegant physical laws governing stellar evolution, planetary motion, and biological processes, suggesting that even in the realm of ultimate uncertainty, some deeper order was preparing to emerge and guide the universe toward the magnificent complexity we observe today, forever linking this ancient moment of quantum foam to every heartbeat, every thought, every wonder you experience in your journey through the submos. Now, as we drift deeper into this primordial mystery, consider what matter actually signified during those first incomprehensible moments when the very concept of mass simply had no meaning, where particles as we know them couldn't exist because the fundamental property that gives things, weight, substance, and resistance to acceleration hadn't yet crystallized from the cosmic potential swirling through this newborn realm. Picture a reality where electric charges held no significance, where the positive and negative polarities that drive every circuit, every lightning bolt, every neural impulse firing in your brain right now existed only as unrealized possibilities within a unified field that contained all electrical potential without expressing any of it. Take a slow breath and contemplate how space and time, those seemingly eternal coordinates that frame every experience you've ever had, every step you've taken, every second that has passed since you were born, simply didn't operate according to the rules we recognize today, instead forming a fluid dynamic substrate where distances and durations fluctuated wildly according to quantum principles that make our everyday geometry seem like a gentle approximation of something far more profound and strange. According to research from theoretical physicists at institutions like Harvard and Oxford, what existed during this epoch was pure energy in its most fundamental manifestation. Not the kinetic energy of moving objects or the thermal energy of hot gases, but something more basic that contained within itself every possible form energy could later assume, from the nuclear fusion powering distant stars to the biochemical processes sustaining life on Earth. Imagine energy so primal it hadn't yet learned to disguise itself as the matter, existing instead as raw creative potential that held within its essence all the information needed to construct protons, electrons, photons, and every other particle that would eventually populate the cosmic zoo. We observe through our most sophisticated telescopes and particle accelerators. What scientists find most intriguing about this phase is that quantum fluctuations provided the only semblance of structure in this cosmic foam, tiny ripples in the fabric of reality that appeared and vanished faster than any measurement could capture, yet somehow carried within their brief existence the blueprints for galactic superclusters and the intricate molecular machinery of living cells. These fluctuations represented something extraordinary, temporary wrinkles in space-time that emerged from pure vacuum energy, creating momentary patterns that would later serve as seeds for all the complexity we see today. From spiral galaxies spinning through the void to the elegant double helix of DNA encoding the instructions for consciousness itself. Research conducted at facilities like Fermilab and CERN suggests that these quantum undulations occurred at scales so minute they make atomic nuclei seem enormous by comparison. Yet their influence would ripple forward through cosmic history, eventually manifesting as the slight density variations that gravitational forces would amplify into the cosmic web of dark matter, filaments connecting galaxy clusters across billions of light years. Consider how remarkable it is that during this phase, before particles had names, before forces had learned to be distinct, before space had learned to be separate from time, the universe somehow contained within its quantum foam all the mathematical relationships that would later govern everything from planetary orbits to the chemical bonds holding your body together, suggesting that even in this realm of ultimate uncertainty, some deeper order was preparing to unfold, carrying within each fleeting fluctuation the potential for stars to shine, planets to form, and minds to wonder about their own cosmic origins in moments like this one. When you pause to contemplate the magnificent mystery of existence itself, how do you break something that was never meant to break? Tonight, we venture into the moment when perfect unity shattered for the first time, when the cosmic superforce that had held all interactions in seamless harmony suddenly fractured, allowing gravity to peel away from its siblings and begin its eternal dance as the architect of cosmic structure. Picture this extraordinary transformation as temperatures plummeted from the unimaginable heights of the Planck era down to a mere 10 to the 27th Kelvin, still incomprehensibly hot by any earthly standard, yet cool enough for the universe to experience its first great symmetry breaking, the initial crack in the perfect mirror of primordial unity. Close your eyes and imagine gravity awakening to its own identity, no longer indistinguishable from the other fundamental interactions, but emerging as a distinct force with its own character, its own rules, its own destiny to bend space-time and gather matter into the magnificent cosmic architecture we observe today. What remained after this cosmic divorce was something physicists call the electronuclear force, a still unified trinity binding together what we now recognize as electromagnetism, the strong nuclear interaction, and the weak nuclear process, three powers that would continue their cosmic partnership for just a little longer, before they too would learn to be separate. According to calculations from theoretical physicists at institutions like Caltech and the Institute for Advanced Study, this moment marked the emergence of recognizable space-time, where the quantum foam of the Planck Epoch began crystallizing into something resembling the geometric framework that would eventually host galaxies, stars, and planets. Though space and time were still far more fluid and dynamic than anything we experience in our everyday existence. Consider how remarkable it is that even after this monumental separation, the entire observable universe still occupied a region smaller than an atomic nucleus, compressed into dimensions so minute that every particle destined to form your body, every photon that would someday carry starlight to your eyes, every quantum of energy that would power 1 trillion suns, remained squeezed into a space that modern microscopes couldn't hope to resolve. Research from cosmologists at Princeton and Cambridge suggests that Gravity's emergence as an independent force fundamentally altered the cosmic landscape, introducing for the first time the possibility of attractive interactions that could pull matter together, setting the stage for the eventual formation of cosmic structure, while the other forces remained locked in their electromagnetic strong-weak alliance. Picture this nascent gravitational field as it began to feel its way through the cosmic foam, learning to respond to energy density, discovering how to curve space-time, preparing to become the invisible hand that would one day guide gas clouds into stellar nurseries and stellar remnants into the supermassive black holes lurking at galactic centers. What fascinates researchers most profoundly about this epoch is how gravity's liberation from the unified superforce immediately began influencing the expansion dynamics of the universe itself, subtly modifying how space stretched and time flowed, creating the foundation for everything from the gentle spiral arms of distant galaxies to the precise orbital mechanics that keep Earth at just the right distance from our Sun to sustain the chemistry of life. As data from cosmic microwave background observations by satellites like Planck and WMAP confirm, this early symmetry breaking left subtle fingerprints in the fabric of space-time, tiny variations in density and curvature that would eventually grow under gravitational influence into the cosmic web of dark matter filaments connecting clusters of galaxies across billions of light years, all stemming from this first moment when the universe learned that unity, however beautiful, was not its ultimate destiny, but rather the starting point for an even more magnificent story of cosmic evolution and increasing complexity. As we follow that idea deeper into this extraordinary epoch spanning from 10 to the negative 43rd seconds through 10 to the negative 36th seconds, we encounter the grand unified theory era, a cosmic phase where three fundamental forces continued their intimate partnership as the electronuclear interaction, while gravity had already begun its solitary journey through space-time. Picture this primordial realm where the strong nuclear force that binds atomic cores, the weak nuclear process governing radioactive decay, and electromagnetism that powers everything from lightning to neural impulses existed as facets of a single magnificent interaction, unified in ways that theoretical physicists at institutions like MIT and Stanford had spent decades attempting to describe through elegant mathematical frameworks. Take a slow breath and contemplate the exotic menagerie of particles that theoretical models predict could have flourished during this phase, including magnetic monopoles, hypothetical entities that would carry isolated north or south magnetic charges rather than the paired poles we observe in every atom. Magnet today, along with other strange species that have never been detected in our modern laboratories but may have danced through the cosmic plasma during these earliest moments. Consider how different reality was when no stable matter could exist, because temperatures remained so ferociously high that any attempt by particles to bind together was instantly shattered by the violent thermal energy surging through every cubic centimetre of space, creating conditions where protons, neutrons, electrons, and all familiar building blocks of atoms remained impossible dreams, rather than tangible realities. According to research from cosmologists at places like the Perimeter Institute and Cambridge, this era exhibited perfect symmetry where all directions in space held equivalent status, meaning that the laws of physics looked identical whether you travelled north, south, east, west, up, down, or any other conceivable direction through the cosmic medium, a beautiful mathematical harmony that our modern universe has lost forever. What captivates scientists most profoundly about this period is how the electronuclear force governed all interactions except gravity, creating a cosmic democracy where electromagnetic attraction, strong nuclear binding, and weak nuclear transformations operated as aspects of one underlying principle, suggesting that beneath the apparent diversity of modern physics lies a deeper unity waiting to be rediscovered through advanced theories and more sophisticated experiments. Imagine the cosmic landscape during this phase as a seething cauldron, where virtual particles materialized and vanished in cascades of creation and annihilation, where the boundary between energy and matter blurred beyond recognition, where every quantum field fluctuated with amplitudes that would make modern particle accelerators seem gentle by comparison. Research conducted at facilities like CERN and Fermilab attempts to recreate tiny echoes of these conditions by colliding particles at tremendous velocities, hoping to glimpse the unified interactions that once dominated cosmic evolution. Though even our most powerful machines can only approximate a fraction of the energy densities that characterized this primordial epoch. Picture how the perfect spatial symmetry of this era meant that concepts like preferred directions, fixed reference frames, or absolute orientations simply didn't exist, creating a cosmic environment where the laws of nature exhibited a mathematical beauty and elegance that would gradually become hidden as the expanding universe cooled and subsequent symmetry-breaking events introduced the apparent complexity and asymmetry we observe in modern physics. According to theoretical predictions from grand unified theories developed by physicists like Sheldon Glashow and Abdus Salem, this epoch should have produced equal quantities of matter and antimatter. Yet somehow a subtle asymmetry emerged that would later tip the cosmic balance in favour of the ordinary particles that compose every star, planet and living creature we know today. What remains most mysterious about this phase is how three distinct forces could operate as one unified interaction while still containing within their mathematical structure the information needed to eventually separate into the electromagnetic force governing atomic chemistry, the strong force binding nuclear cores, and the weak force enabling stellar nucleosynthesis, suggesting that even in perfect unity, the seeds of diversity were already present, waiting for the right moment to unfold and create the rich tapestry of interactions that would eventually enable galaxies to form, stars to ignite, and consciousness to emerge from the cosmic dance of particles and fields. Now, as we drift deeper into this cosmic mystery, we encounter the most puzzling chapter in the universe's origin story, where an almost imperceptible bias emerged that would determine whether anything we recognize today could ever exist at all. A subtle preference for matter over antimatter that scientists call baryogenesis, the cosmic conspiracy that ensured every atom in your body would survive the mutual annihilation that should have left the cosmos empty and dark. Picture this extraordinary moment when the fundamental conservation laws that govern modern physics may have experienced their only known violation, allowing the perfect balance between particles and antiparticles to shift by just 1 part in 10 billion, a deviation so tiny it seems insignificant yet profound enough to account for every star shining in the night sky, every planet orbiting through space, every molecule of water that has ever existed on Earth. Take a slow breath and contemplate how temperatures continued their relentless decline from 10 to the 27th Kelvin down to 10 to the 24th Kelvin, still unimaginably hot by terrestrial standards but cool enough for the cosmic environment to prepare for its next dramatic transformation, setting the stage for processes that would fundamentally reshape reality itself. According to theoretical frameworks developed by physicists like Andrei Sakharov and research conducted through NASA's Theoretical Astrophysics Division, this epoch represents the universe's first brush with asymmetry, the initial crack in the perfect mirror of cosmic democracy that had characterized earlier phases, introducing for the first time the possibility that nature might favor one outcome over another in ways that would prove essential for the eventual emergence of complexity and structure. Consider how the expanding universe served as a cosmic refrigerator during this phase, steadily reducing the energy density as space itself stretched, diluting the thermal chaos that had prevented any stable relationships between particles, while simultaneously creating the conditions needed for more organized interactions to emerge from the quantum maelstrom. What fascinates cosmologists most profoundly is how this seemingly random fluctuation in the matter-antimatter balance may have been orchestrated by exotic processes involving particles and interactions that have never been directly observed, perhaps through the decay of massive bosons, or the CP violation phenomena that Nobel laureates James Cronin and Val Fitch discovered in laboratory experiments decades later. Research from institutions like ESA's Theoretical Cosmology Group suggests that this epoch established the foundational imbalance that would cascade through all subsequent cosmic evolution, ensuring that when protons and antiprotons eventually collided in the cosmic furnace, when electrons and positrons met their mutual destruction, a tiny residue of ordinary matter would survive to become the raw material for galaxies, solar systems, and the intricate biochemistry of life itself. Picture the universe during this phase as a cosmic courtroom, where the laws of physics themselves were on trial, where the conservation principles we consider sacred and inviolable may have bent just enough to allow existence as we know it to emerge from what should have been perfect annihilation, creating a cosmic exception that makes every sunrise possible, every heartbeat meaningful, every thought you're thinking right now a direct descendant of this ancient asymmetry. According to data analysis from cosmic microwave background observations and Big Bang nucleosynthesis models, this epoch set up everything that followed, from the formation of the first atomic nuclei to the ignition of primordial stars, establishing the cosmic inventory of matter that would eventually cool into planets, crystallize into minerals, and organize into the biological molecules that carry genetic information across generations. What remains most mysterious about this phase is how such a small violation of fundamental symmetry could have such enormous consequences, suggesting that the universe operates according to principles where tiny causes can have vast effects, where quantum-scale events during the first microseconds after creation continue to influence the largest structures we observe through our most powerful telescopes billions of years later. As the universe continued its expansion and cooling, approaching the critical threshold where new forms of organization would become possible, this matter-antimatter asymmetry represented the cosmic decision that made all future complexity achievable, ensuring that instead of empty space filled only with photons, the cosmos would teem with the particles needed to construct atomic nuclei, stellar cores, planetary atmospheres, and eventually the conscious observers capable of contemplating their own improbable existence in this vast and magnificent cosmic theatre. What happens when the universe grows up faster than light itself? Tonight we witness the most spectacular growth spurt in cosmic history, as the grand unified theory symmetry finally shattered and the strong nuclear force broke free from its partnership with electromagnetism and the weak interaction, triggering an explosion of space-time expansion so violent and rapid that reality itself stretched beyond every boundary previously imagined. Picture this moment of cosmic liberation when the strong force destined to become the mighty architect binding quarks into protons and neutrons suddenly separated from the electroweak duo, releasing such tremendous energy that it powered the most extraordinary phase transition the universe would ever experience. An event so dramatic it makes stellar explosions seem gentle by comparison. Close your eyes and contemplate the mysterious inflaton field, a hypothetical entity that theoretical physicists at institutions like Stanford and MIT propose as the driving mechanism behind this cosmic metamorphosis, an invisible presence that permeated every corner of space and carried within its quantum fluctuations the power to reshape reality on scales that dwarf galaxies and stretch across billions of light years. Take a slow breath as you consider how the universe transformed during this incredible epoch, growing from dimensions smaller than a subatomic particle to macroscopic scales in just 10 to the negative 32nd seconds, expanding by a factor of 10 to the 26th power, a number so vast that if you started with something the size of a proton and applied this same growth factor, it would become larger than a basketball in less time than light takes to cross an atomic nucleus. According to research from cosmologists at places like the Perimeter Institute and Cambridge, this exponential expansion solved some of the deepest mysteries in astrophysics, explaining why the cosmic microwave background radiation appears so uniform across the sky despite originating from regions that should never have been in thermal contact, and why the geometry of space-time measures so precisely flat, even though most theoretical models predict curved cosmic architectures. What captivates scientists most profoundly about this phase is how the inflaton field managed to maintain its energy density even as space expanded exponentially, unlike ordinary matter and radiation, which become diluted as the volume increases, creating a cosmic engine that could sustain its own fuel supply while driving the most magnificent expansion event in natural history. Imagine the cosmic landscape during these brief moments when distances doubled and redoubled with such ferocious speed that quantum fluctuations in the inflaton field were stretched from microscopic ripples into variations large enough to eventually become the seeds of galactic superclusters, transforming tiny quantum uncertainties into the cosmic web of dark matter filaments that connects galaxy clusters across the observable universe today. Research conducted at facilities like CERN and theoretical investigations at Princeton suggest that this inflationary epoch represents the universe learning to transcend the speed limit imposed, by light, not by moving matter faster than photons can travel, but by expanding the very fabric of space-time itself, creating new distance without anything actually moving through space in the conventional sense. Picture how this process unfolded as the strong force discovered its independence, no longer bound to electromagnetic and weak interactions, but free to develop its own character, its own rules, its own destiny to become the cosmic glue that would eventually hold atomic nuclei together against electromagnetic repulsion, enabling the formation of elements heavier than hydrogen and making chemistry possible. According to data from cosmic microwave background observations by satellites like Planck and WMAP, the quantum fluctuations that occurred during inflation left permanent imprints on the structure of space-time, tiny variations in density and curvature that we can still observe today as temperature differences in the ancient radiation that fills the cosmic background, providing direct evidence for this remarkable phase of exponential growth that occurred when the universe was still younger than the time it takes light to cross a single atom. What remains most astonishing about this epoch is how such a brief interval, lasting less time than it takes for the strongest electromagnetic pulse to traverse the smallest distances we can measure, managed to establish the fundamental architecture of everything we observe through our most powerful telescopes, from the largest cosmic voids to the densest galaxy clusters, all stemming from quantum seeds planted during these first moments when space-time itself learned to expand faster than the cosmic speed limit. As we follow that idea deeper into this magnificent cosmic metamorphosis, we encounter the most extraordinary aspect of inflation, space-time itself expanding faster than photons could travel, not by accelerating matter through existing dimensions, but by creating new distance between every point in the universe, stretching the very coordinates of reality at speeds that make light seem sluggish by comparison. Picture this remarkable phenomenon solving one of cosmology's greatest puzzles, the horizon problem, which had troubled scientists who wondered how regions of space separated by distances light could never have crossed, during the early universe managed to reach identical temperatures, creating the uniform cosmic microwave background radiation we observe today across the entire sky. Close your eyes and contemplate how this same process resolved the flatness problem, another cosmic mystery concerning why space-time exhibits such precise geometric properties when most theoretical models predicted curved architectures that would have caused the universe to either collapse immediately or expand so rapidly that no structure could ever form. Take a slow breath as you consider the quantum fluctuations that existed at microscopic scales before inflation suddenly stretched them across cosmic distances, transforming tiny uncertainty ripples in fundamental fields into variations spanning light years, creating the density differences that would eventually grow under gravitational influence into the magnificent cosmic web of galaxies and dark matter filaments we observe through our most powerful telescopes today. According to research from theoretical physicists at institutions like Harvard and Princeton, these microscopic quantum seeds embedded during inflation carry within their mathematical structure all the information needed to explain why galaxies cluster in particular patterns, why cosmic voids exist where they do, and how the largest structures in the universe arrange themselves according to principles that trace back to quantum mechanics operating at subatomic scales during this brief epoch of exponential growth. What fascinates cosmologists most profoundly is how the universe transformed from electron-sized dimensions to golf ball proportions in an instant so brief that electromagnetic radiation couldn't even begin to cross the expanding realm. Yet this transformation established the foundational architecture for everything from spiral arms in distant galaxies to the precise distribution of matter that would eventually enable solar systems to form in stable configurations capable of supporting planetary atmospheres and biological evolution. Imagine the cosmic landscape during these moments, when space-time learned to stretch in ways that preserved causal relationships while simultaneously solving fundamental problems in physics, creating a universe where distant regions could share common properties despite being separated by distances that preclude any form of communication or interaction according to Einstein's speed limit for information transfer. Research conducted through cosmic microwave background observations by satellites like Planck and WMAP confirms that these quantum fluctuations stretched during inflation left permanent fingerprints in the fabric of reality, tiny temperature variations that we can measure today with extraordinary precision, providing direct observational evidence for this remarkable phase when the universe grew faster than its own light could travel. Picture how this process embedded the seeds of cosmic structure throughout space-time, ensuring that billions of years later, when gravitational forces had time to amplify these initial density differences, galaxies would form in precisely the locations and configurations needed to create environments where stars could ignite, planets could coalesce, and the chemistry of life could eventually emerge from the cosmic dance of atoms and molecules. According to theoretical frameworks developed by cosmologists like Alan Guth and Andre Linde, inflation represents the universe's solution to its own initial conditions problem, creating through exponential expansion the specific circumstances needed for complexity and organization to eventually emerge from what would otherwise have been chaotic thermal equilibrium throughout cosmic history. What remains most remarkable about this epoch is how the quantum nature of reality at the smallest scales became imprinted on the largest structures we can observe, suggesting that the universe operates according to deep principles where microscopic uncertainties and macroscopic architectures are intimately connected through the cosmic expansion that began during these first moments after the strong force learned to be independent. As inflation finally ended and the universe prepared for its next phase of evolution, the cosmic seeds planted during this extraordinary expansion would continue to influence structure formation for billions of years, eventually leading to the emergence of stellar nurseries, planetary systems, and the intricate molecular processes that enable conscious observers to contemplate their own improbable existence in this vast and magnificent cosmic theatre that grew from quantum foam to cosmic majesty faster than light itself could witness the transformation. Now, as we drift deeper into this cosmic epoch of exponential transformation, consider what actually populated the universe during these extraordinary moments when reality stretched beyond all comprehension, dominated entirely by the enigmatic inflaton field that permeated every cubic centimetre of expanding space-time, with energy so intense it dwarfed any force we observe in modern physics. Picture this mysterious entity as it commanded the cosmic stage, its energy density remaining constant even as space itself multiplied exponentially, creating the paradoxical situation where the total amount of energy in the universe increased dramatically while the field maintained its uniform intensity throughout the rapidly growing volume. Close your eyes and contemplate the vacuum energy that served as the cosmic engine driving this magnificent expansion. Not the empty nothingness we might expect from the word vacuum, but rather a seething reservoir of potential that contained within its quantum structure all the power needed to reshape reality on scales that would eventually encompass billions of galaxies scattered across cosmic distances. Take a slow breath as you consider how primitive spacetime provided the rapidly expanding geometric framework for everything that would follow, still far more dynamic and fluid than the relatively stable arena we experience today, yet already beginning to establish the mathematical relationships between distance, duration, and curvature that would eventually govern planetary orbits and stellar evolution. According to research from theoretical physicists at institutions like MIT and Stanford, quantum fluctuations during this phase operated as cosmic architects, creating the blueprints for all future structure by introducing tiny variations in the inflaton field that would be stretched to astronomical proportions, ensuring that billions of years later matter would clump into galaxies and stars rather than remaining perfectly distributed throughout space. What captivates cosmologists most profoundly is how these fluctuations emerged from the fundamental uncertainty principle governing quantum mechanics, where the very act of trying to measure position and momentum simultaneously creates unavoidable ripples in any field, meaning that the universe could not remain perfectly smooth even in principle, guaranteeing that some form of cosmic architecture would eventually emerge from this primordial chaos. Imagine the absence of particles as we know them during this epoch, where temperatures remained far too extreme for stable matter to exist, yet the inflaton field carried within its quantum oscillations all the information needed to eventually produce protons, electrons, photons, and every other species in the particle zoo that populates our modern cosmos. Research conducted at facilities like CERN and theoretical investigations at Princeton suggest that while recognizable particles couldn't survive in these conditions, the mathematical relationships governing their future properties were already encoded in the field dynamics, waiting for cooler temperatures to allow their manifestation as discrete entities with mass, charge, and seat. Picture how temperatures began their gradual decline from the incomprehensible heights of earlier epochs, still remaining unimaginably hot by any terrestrial standard, but slowly approaching thresholds where new forms of organization would become possible, setting the stage for the next dramatic transformation in cosmic evolution. According to data from cosmic microwave background observations by satellites like Planck and WMAP, the quantum fluctuations that occurred during inflation left permanent signatures in the structure of spacetime, creating patterns that we can still observe today as tiny temperature variations in the ancient radiation that fills the cosmic background, providing direct evidence for the remarkable processes that shaped reality during these earliest moments. What remains most mysterious about this phase is how the inflaton field managed to maintain its energy density throughout the exponential expansion, apparently violating the normal expectation that energy becomes diluted as volume increases, suggesting that this entity operated according to principles that transcend our everyday understanding of conservation laws and thermodynamics. Consider how the primitive spacetime of this era gradually evolved towards something resembling the stable geometric framework we observe today, yet retained enough quantum dynamism to support the field fluctuations that would become the seeds of galactic superclusters, creating a cosmic environment where order and chaos dance together in patterns that would influence structure formation for billions of years. As this remarkable epoch drew toward its conclusion, the inflaton field prepared to decay into ordinary particles and radiation, transforming its concentrated energy into the diverse menagerie of matter and forces that would populate the next phase of cosmic evolution, forever linking these moments of exponential growth to every atom in your body, every photon reaching your eyes from distant stars, every quantum process enabling the consciousness that contemplates these magnificent mysteries of existence itself. What does the universe look like when it's a perfect liquid? Tonight we witness the moment when cosmic inflation finally exhausted itself, and the inflaton field began its magnificent decay, transforming concentrated vacuum energy into the first genuine particles and radiation that would populate reality, marking the end of exponential expansion and the beginning of a new chapter where matter and antimatter dance together in the most extraordinary fluid ever to exist. Picture this cosmic transformation as temperatures soared to 10 to the 12th Kelvin during the reheating process, still unimaginably hot by terrestrial standards, yet cool enough for the universe to support its first stable population of fundamental particles, creating conditions where quarks and gluons could emerge as distinct entities rather than remaining dissolved in the unified quantum foam of earlier epochs. Close your eyes and contemplate the birth of the first real matter and antimatter, not the virtual particles that flickered in and out of existence during previous phases, but genuine physical entities with measurable properties, mass, charge, and spin flooding the cosmic arena with a menagerie of particles that included quarks in 6 different flavors, electrons and positrons, photons carrying electromagnetic radiation, and exotic species that have no modern equivalents. Take a slow breath as you consider how the quark epoch began during this remarkable phase, introducing the fundamental building blocks that would eventually be confined within protons and neutrons, yet during these early moments existed as free agents swimming through a cosmic soup with properties so unusual that modern physics laboratories spend billions of dollars trying to recreate tiny droplets of this primordial substance. According to research conducted at facilities like CERN and Brookhaven National Laboratory, this cosmic fluid exhibited the characteristics of a perfect liquid, flowing with lower viscosity than any known substance, moving with such frictionless ease that it defied the expectations of physicists who had predicted a gaseous state for liberated quarks and gluons. What captivates scientists most profoundly about this phase is how the strong force, having recently separated from electromagnetic and weak interactions, learned to operate in an entirely new regime where its carriers, the gluons, could propagate freely through space rather than being confined within individual particles, creating a cosmic medium where the fundamental interactions governing atomic nuclei existed in a state of liberation unknown in our modern universe. Imagine the cosmic landscape during these moments, when matter and antimatter appeared in roughly equal quantities, yet the slight asymmetry established during earlier symmetry breaking events ensured that ordinary particles would eventually outnumber their antiparticle partners by just enough to account for every atom that would ever exist, from the hydrogen fueling distant stars to the carbon forming the backbone of biological molecules. Research from theoretical physicists at institutions like MIT and Princeton suggests that this perfect fluid behavior emerged because quarks and gluons, when freed from confinement, interact so strongly with each other that they form an almost ideal medium, where energy and momentum transfer with extraordinary efficiency, creating flow patterns that would make the most advanced supercomputers struggle to simulate accurately. Picture how this quark-gluon plasma filled the entire observable universe, extending across regions that would eventually become separated by billions of light years, yet during this epoch remained in thermal equilibrium, maintaining uniform temperature and pressure throughout its vast extent while containing within its seething depths all the raw material needed to construct galaxies, stars, planets, and the intricate molecular machinery of life itself. According to data from cosmic microwave background observations and particle physics experiments, this epoch represents the universe learning to support complex many-body interactions for the first time, where individual particles could influence each other through the strong force while electromagnetic and weak interactions added their own subtle contributions to the cosmic choreography. What remains most remarkable about this phase is how such an apparently chaotic soup of fundamental particles somehow contained within its quantum dynamics all the information needed to eventually produce the ordered structures we observe today, suggesting that even in this realm of maximum entropy and thermal equilibrium, deeper organizing principles were already preparing to manifest as temperatures continued to cool and new forms of cosmic architecture became energetically favorable, setting the stage for the next dramatic transformation when quarks would learn to be confined within stable composite particles for the first time in cosmic history. As we follow that idea deeper into this cosmic cauldron, we encounter the most extraordinary soup ever to exist, where quarks and gluons swam freely through space-time, unconfined by the strong force that would later imprison them within protons and neutrons, creating a primordial ocean of fundamental particles that behaved unlike anything we observe in our modern universe. Picture these liberated quarks existing in 6 distinct flavors that physicists have playfully named up, down, strange, charm, bottom, and top, each carrying unique properties of mass and electric, charge dancing together in combinations that would be impossible once temperatures cooled enough for confinement to take hold and lock them permanently inside composite particles. Close your eyes and contemplate the remarkable color charges that each quark possessed. Not actual hues visible to human perception, but quantum properties designated red, green, and blue by scientists who needed labels for the three-way symmetry governing strong interactions, creating a cosmic rainbow of possibilities where particles could combine according to rules as precise and beautiful as any artistic masterpiece. Take a slow breath as you consider the gluons threading through this primordial medium, serving as carriers of the strong force while themselves carrying color charge, making them unique among the fundamental interactions because they could interact directly with each other rather than merely mediating between other particles, creating cascades of self-reinforcing effects that gave the cosmic plasma its extraordinary fluid properties. According to groundbreaking research conducted at CERN's Large Hadron Collider and Brookhaven National Laboratory's Relativistic Heavy Ion Collider, experiments that smash gold nuclei together at nearly light speed have successfully recreated tiny droplets of this ancient substance, confirming that the early universe indeed behaved like a perfect liquid, with viscosity lower than any known material, flowing with such ideal characteristics that it challenges our understanding of how complex many-body systems should operate under extreme conditions. What captivates particle physicists most profoundly about this epoch is how the strong force operated in complete transparency, allowing quarks to see and interact with partners separated by cosmic distances rather than being confined within individual hadrons, creating conditions where the fundamental interaction governing atomic nuclei existed in a state of perfect democracy throughout the expanding universe. Imagine the cosmic landscape during these microseconds when every type of quark roamed freely alongside their antimatter counterparts, when strange quarks with their unusual properties mixed with more familiar up and down varieties, when charm, bottom, and top quarks added their exotic characteristics to the seething mixture, creating particle combinations that would be energetically impossible once the universe cooled and stabilized into its modern configuration. Research from theoretical physicists at institutions like MIT and Princeton indicates that this quark-gluon plasma exhibited collective behavior, where individual particles lost their separate identities and merged into a coherent fluid, moving together with such coordination that density waves could propagate across vast distances, setting up acoustic oscillations that would later become imprinted on the cosmic microwave background radiation as evidence of these ancient sound waves echoing through the primordial cosmos. Picture how modern experiments at these particle accelerators provide our only direct glimpse into cosmic conditions from nearly 14 billion years ago, creating fireballs lasting mere moments, but hot enough to melt protons and neutrons back into their constituent quarks, allowing scientists to study the properties of matter that existed when the entire observable universe was younger than the time it takes light to cross a single atom. According to data from these sophisticated experimental programs, the perfect fluid behavior emerges because quarks and gluons, when liberated from confinement, interact so strongly that they achieve thermal equilibrium almost instantaneously, creating a medium where energy and momentum flow with extraordinary efficiency while maintaining the quantum correlations that would eventually enable the formation of stable composite particles. What remains most astonishing about this phase is how such apparent chaos somehow contained the seeds of cosmic order, where the same strong force that allowed perfect fluidity would soon learn to confine quarks permanently within hadrons, transforming this era of maximum freedom into the structured particle zoo that populates our modern universe, forever linking these moments of liberation to every proton in your body, every neutron in atomic nuclei, every nuclear reaction powering the stars that illuminate the night sky with ancient light. Now, as we drift deeper into this remarkable cosmic phase, consider how the fundamental architecture of reality finally assumed the configuration we recognize today, with 4 distinct forces governing all interactions throughout the universe: gravity sculpting the large-scale structure of space-time, electromagnetism orchestrating the dance of charged particles, the strong nuclear interaction binding quarks within hadrons, and the weak nuclear process enabling certain types of radioactive transformations. Picture this cosmic moment when 3 of these forces had achieved their modern identities while electromagnetism and the weak interaction remained partners in their electro-weak alliance, still sharing a unified mathematical description that would persist until temperatures dropped below the critical threshold, where their final separation could occur. Close your eyes and contemplate the constant creation and annihilation of particle-antiparticle pairs throughout this seething cosmic medium, where electrons and positrons materialize from pure energy before finding each other again in flashes of mutual destruction, where quarks and antiquarks emerged from the quantum vacuum only to collide moments later in bursts of electromagnetic radiation, creating a dynamic equilibrium between matter and energy that maintained perfect balance across the expanding universe. Take a slow breath as you consider how thermal equilibrium governed this cosmic symphony, ensuring that energy remained perfectly distributed among all particle species, despite their constant creation and destruction, maintaining temperatures that fluctuated between 10 to the 12th Kelvin and 10 to the 9th Kelvin as the universe continued its relentless expansion and cooling. According to research from theoretical physicists at institutions like Harvard and Princeton, this epoch represents the universe achieving its first stable configuration, where all fundamental interactions operated according to the mathematical frameworks we use to describe modern particle physics, creating conditions where scientists can apply quantum field theory and the Standard Model to understand cosmic evolution with remarkable precision and accuracy. What captivates cosmologists most profoundly about this phase is how nearly 1/1,000,000th of a second, an interval that seems fleeting by human standards, constituted an eternity in cosmic terms during these early moments when physical processes operated at speeds limited only by the fundamental constants governing electromagnetic and strong interactions. Imagine the cosmic landscape during these microseconds when particle physics experiments conducted in terrestrial laboratories can directly recreate the conditions that filled the entire observable universe, allowing scientists at facilities like CERN and Fermilab to peer backward through cosmic time by studying the behavior of matter under extreme temperatures and densities that mirror these ancient epochs. Research conducted through high-energy particle collisions confirms that the electroweak force maintained its unified character throughout this period, with W and Z bosons mediating interactions between leptons and quarks, according to the mathematical symmetries discovered by physicists like Sheldon Glashow, Steven Weinberg, and Abdus Salam, who shared the Nobel Prize for revealing the deep connections between electromagnetic and weak nuclear phenomena. Picture how the 4 forces operated in perfect harmony during this phase, each contributing its unique character to the cosmic symphony, while respecting the precise mathematical relationships that govern their relative strengths and interaction ranges, creating a universe where structure formation could proceed according to predictable physical laws rather than chaotic randomness. According to data from cosmic microwave background observations and Big Bang nucleosynthesis models, This epoch established the final configuration of fundamental interactions that would persist throughout subsequent cosmic evolution, ensuring that nuclear fusion in stellar cores, chemical bonding in planetary atmospheres, and electromagnetic processes in biological systems would all operate according to the same physical principles that govern the primordial plasma filling space during these earliest microseconds. What remains most remarkable about this phase is how the universe managed to maintain perfect thermal equilibrium among vastly different particle species while constantly creating and destroying matter at rates that would make modern particle accelerators seem sluggish, suggesting that the cosmic medium possessed self-regulating properties that automatically balanced energy flow and maintained stable conditions, even as expansion continued to cool and dilute the primordial soup. As this extraordinary epoch drew toward its conclusion and temperatures approached the threshold where new forms of organization would become possible, the stage was perfectly set for the next dramatic transformation in cosmic evolution, when quarks would finally be confined within stable composite particles and the modern era of nuclear physics would begin its magnificent journey towards stars, planets, and conscious life contemplating the cosmos. When did the universe's particles first learn to hold hands? Tonight we witness one of the most dramatic transformations in cosmic history as temperatures finally dropped below 2 trillion Kelvin, crossing the critical threshold of our 70 mega-electron volts, where the strong force suddenly shifted from enabling perfect fluidity to demanding absolute confinement, forcing quarks to abandon their ancient freedom and bind together into the first stable composite particles that would populate the universe for billions of years to come. Picture this extraordinary moment when quarks, having roamed freely through the cosmic plasma for nearly a microsecond, suddenly found themselves trapped by an invisible prison made of pure force, unable to exist as isolated entities because the strong interaction had learned a new trick called color confinement that made separation energetically impossible. Close your eyes and contemplate the birth of the first protons, as 2 up quarks and 1 down quark discovered how to combine their electric charges and masses into a stable trinity that would become the fundamental building block of atomic nuclei, carrying within its compact structure the potential to form hydrogen, the simplest element and most abundant substance in the cosmos. Take a slow breath as you consider how neutrons emerge through a slightly different arrangement, where 1 up quark joined 2 down quarks to create an electrically neutral particle with nearly identical mass to its proton cousin, yet possessing the remarkable ability to bind with protons through the residual strong force that would eventually enable the formation of every element heavier than hydrogen. According to research from particle physicists at institutions like CERN and Fermilab, this epoch also witnessed the appearance of mesons, exotic particles formed from quark-antiquark pairs that created temporary species like pions and kaons, unstable entities that would decay rapidly but play crucial roles in mediating the nuclear interactions that bind atomic cores together in stable configurations. What captivates scientists most profoundly about this phase is how color confinement emerged as an absolute law of nature, making it impossible for quarks to exist alone because the strong force actually grows stronger with distance, unlike electromagnetic or gravitational interactions that weaken as objects separate, creating a cosmic rule that ensures quarks must always appear in color-neutral combinations. Imagine the cosmic landscape during these moments, when the universe transformed from a sea of free quarks and gluons into a structured medium filled with hadrons, baryons like protons and neutrons that contain 3 quarks each, and mesons that temporarily house quark-antiquark pairs before decaying into lighter particles and energy. Research conducted through high-energy particle collisions at facilities like Brookhaven National Laboratory confirms that this transition occurred suddenly and completely, with no intermediate phase where partially confined quarks could exist, suggesting that the strong force operates according to all-or-nothing principles that brook no compromise between freedom and bondage. Picture how this confinement process preserved the quantum properties of individual quarks while hiding them forever inside composite particles, ensuring that the fractional electric charges, exotic flavors, and color properties that characterize the quark-gluon plasma would remain accessible only through indirect measurements and high-energy experiments designed to probe the interior structure of protons and neutrons. According to theoretical frameworks developed by quantum chromodynamics pioneers like Murray Gell-Mann and Harold Fritsch, This phase represents the universe learning to hide its fundamental complexity behind a facade of apparent simplicity, where the rich dynamics of quark and gluon interactions became masked within particles that behave according to relatively straightforward nuclear physics. What remains most remarkable about this epoch is how the same strong force that had enabled perfect fluidity during the quark-gluon plasma era suddenly reversed its character, transforming from a liberating influence into a confining mechanism that would define the structure of matter for all subsequent cosmic evolution, creating the stable particles needed for nuclear fusion, atomic chemistry, and eventually the biological processes that enable consciousness to contemplate these magnificent transformations. As this extraordinary phase concluded, and the universe filled with its first population of stable composite particles, the stage was perfectly set for the next chapter in cosmic evolution, when electromagnetic and weak forces would finally separate and begin their own specialized roles in governing atomic structure and nuclear processes. As we follow that idea deeper into this cosmic transformation, we witness the final great symmetry breaking in the fundamental forces as electromagnetic and weak nuclear interactions finally learn to be distinct entities after billions of years of unified existence, marking the moment when the universe achieved its modern configuration of 4 separate forces governing all physical phenomena throughout space-time. Picture this extraordinary separation occurring as temperatures continued their relentless decline toward 100 billion Kelvin, cool enough for the electro-weak symmetry to shatter and reveal the hidden differences between forces that had masqueraded as one interaction since the earliest moments after cosmic inflation ended. Close your eyes and contemplate the emergence of W&Z bosons, massive carriers of the weak nuclear force that suddenly materialized with substantial heft, roughly 80 and 91 times heavier than protons respectively, becoming the heavyweight champions of particle physics, while their electromagnetic cousins remained ethereal and massless. Take a slow breath as you consider how photons assume their familiar role as the weightless messengers of electromagnetic interaction, destined to carry light across cosmic distances, transmit energy from stellar cores to planetary surfaces, and enable the intricate electrical processes that power everything from neural networks to technological civilization. According to research from particle physicists at institutions like CERN and the Stanford Linear Accelerator, this epoch witnessed the Higgs mechanism spring into action, endowing particles with their characteristic masses through interactions with an invisible field permeating all of spacetime, creating the mass hierarchy that distinguishes electrons from muons, protons from neutrons, and every other species in the cosmic zoo. What captivates scientists most profoundly about this phase is how 4 distinct fundamental interactions finally established their modern identities, with gravity sculpting large-scale cosmic architecture, electromagnetism governing atomic chemistry and stellar processes, the strong force binding nuclear cores, and the weak interaction enabling radioactive transformations that power stellar nucleosynthesis and geological processes. Imagine the cosmic landscape during these moments when particle masses crystallized into their permanent values, ensuring that electrons would always be precisely 1836 times lighter than protons, that neutrons would outweigh their proton partners by just enough to make nuclear physics possible, and that every subsequent chemical and biological process would operate according to these fundamental mass relationships established during the universe's first second. Research conducted through high-energy experiments at facilities like Fermilab confirms that the electroweak breaking occurred suddenly and completely, with no gradual transition between unified and separated states, suggesting that the universe operates according to phase transitions as dramatic and irreversible as water freezing into ice or steam condensing into liquid droplets. Picture how this separation enabled specialized interactions that would prove essential for cosmic evolution, within electromagnetic forces governing atomic structure and chemical bonding, while weak processes allowed heavy elements to be synthesized in stellar cores through the radioactive transformations that convert hydrogen into helium and eventually produce carbon, oxygen, iron, and all the other elements necessary for planetary formation and biological complexity. According to theoretical frameworks developed by physicists like Steven Weinberg and Sheldon Glashow, this epoch represents the universe achieving its final physical architecture, where all subsequent evolution would proceed according to the 4-force framework that continues to govern cosmic processes today, from the nuclear fusion reactions powering distant quasars to the electromagnetic signals carrying information through your nervous system. What remains most remarkable about this phase is how the universe managed to preserve perfect mathematical relationships between the fundamental interactions even as they separated into distinct entities, maintaining the precise ratios of coupling strengths that allow stars to shine stably, planets to form solid surfaces, and atoms to combine into the complex molecules that enable life to emerge from cosmic chemistry. As temperatures continued dropping toward 10 to the 9th Kelvin and the universe prepared for its next transformation, the stage was perfectly set for nuclear processes to begin, when protons and neutrons would learn to bind together into the first atomic nuclei, and cosmic nucleosynthesis would forge the light elements that would seed stellar formation for billions of years to come. Now, as we drift deeper into this cosmic drama, we witness the most consequential battle in the history of existence as matter and antimatter engaged in their great annihilation event, a mutual destruction so complete that it should have left the universe empty and dark, filled only with photons racing through an eternal void devoid of atoms, stars, planets, or any possibility for complexity to emerge. Picture this extraordinary cosmic genocide where particles and their antiparticle twin stems found each other with devastating precision. Electrons colliding with positrons in brilliant flashes of pure energy. Protons meeting antiprotons in explosive encounters that converted mass directly back into radiation, creating a cosmic furnace where nearly everything that had emerged from the primordial plasma was destined for immediate obliteration. Close your eyes and contemplate the slight asymmetry that saved existence itself, a barely perceptible bias favouring ordinary matter by just one extra particle per billion particle, antiparticle pairs, a deviation so tiny it seems almost accidental yet profound enough to account for every atom in your body, every star shining in distant galaxies, every planet orbiting through space across the observable universe. Take a slow breath as you consider how this minuscule baryon excess, established during the earlier epochs of symmetry breaking, became amplified through the annihilation process to create the cosmic inventory of protons and neutrons that would eventually form atomic nuclei, stellar cores, and the chemical elements necessary for planetary formation and biological evolution. According to research from theoretical physicists at institutions like MIT and Princeton, lepton survival accompanied this baryon rescue, ensuring that electrons and neutrinos would also persist through the cosmic apocalypse in precisely the right numbers to balance electric charges and enable stable atomic structure throughout subsequent cosmic evolution. What captivates cosmologists most profoundly about this phase is how the universe achieved a nearly perfect composition of roughly equal numbers of protons, neutrons, and electrons, creating the ideal conditions for nuclear fusion processes while maintaining electrical neutrality on all scales, from individual atoms to galactic superclusters spanning billions of light years. Imagine the cosmic landscape during these moments when mutual annihilation reached its crescendo, releasing energy equivalent to converting the mass of entire galactic clusters back into pure radiation, yet somehow leaving behind precisely the right amount of ordinary matter needed to construct the complex cosmic architecture we observe through our most powerful telescopes today. Research conducted through Big Bang nucleosynthesis models confirms that this epoch established the perfect setup for the next phase of cosmic evolution, ensuring that the surviving protons and neutrons would exist in optimal ratios for nuclear fusion, while electrons remained available to eventually form neutral atoms once temperatures dropped sufficiently to allow electromagnetic binding. Picture how this cosmic selection process operated with mathematical precision, preserving not only the right total amount of matter, but also the correct proportions of different particle species, creating conditions where hydrogen would dominate the cosmic chemical inventory while helium, lithium, and other light elements could form in exactly the abundances needed to fuel stellar nucleosynthesis and galactic chemical evolution. According to data from cosmic microwave background observations and laboratory measurements of primordial element abundances, this matter-antimatter asymmetry represents one of the greatest mysteries in physics, suggesting that the laws of nature contain subtle biases that favour existence over non-existence, complexity over simplicity, and the rich cosmic tapestry we observe today over the sterile emptiness that pure symmetry would have produced. What remains most astonishing about this epoch is how such an apparently random fluctuation in the fundamental balance between particles and antiparticles managed to create exactly the conditions needed for galaxies to form, stars to ignite, planets to coalesce, and conscious observers to emerge billions of years later, capable of contemplating the magnificent improbability of their own existence in this vast and wonderful cosmic theatre, where matter learned to triumph over antimatter by the narrowest possible margin. How did the universe build its first atomic hearts? Tonight we witness the moment when cosmic temperatures finally dropped to 10 to the 9th Kelvin, cool enough for the strong nuclear force to overcome electromagnetic repulsion and begin forging the first atomic nuclei from individual protons and neutrons, transforming the universe into a gigantic fusion reactor that would operate for exactly 20 minutes before expansion and cooling shut down this primordial atomic foundry forever. Picture this extraordinary epoch when the neutron-to-proton ratio had stabilized at approximately 1:7, a precise balance established by weak nuclear interactions during the preceding seconds, creating the perfect cosmic recipe for nuclear synthesis, while ensuring that hydrogen would dominate the elemental inventory throughout subsequent cosmic evolution. Close your eyes and contemplate the first fusion reaction as a lone proton captured a wandering neutron binding together through the strong force to create deuterium, heavy hydrogen with twice the mass of its lighter cousin, releasing a photon that carried away the excess energy and marked the universe's first successful attempt at nuclear architecture. Take a slow breath as you consider how deuterium formation opened the floodgates for cosmic nucleosynthesis, providing the essential building block that would enable more complex nuclear reactions, yet remaining delicate enough that high-energy photons could easily break these newborn nuclei apart, creating a delicate balance between construction and destruction in the cosmic fusion furnace. According to data from NASA's theoretical nucleosynthesis models and observations of primordial element abundances, this epoch also witnessed the temporary creation of tritium, an unstable isotope containing one proton and two neutrons that would serve as a crucial intermediate step in building heavier elements before eventually decaying back into simpler components. What captivates nuclear astrophysicists most profoundly about this phase is how the entire observable universe operated as a single coordinated fusion reactor, with nuclear processes occurring simultaneously across regions that would eventually become separated by billions of light years, yet maintaining remarkably uniform conditions that produced nearly identical elemental ratios throughout the cosmic medium. Imagine the nuclear landscape during these precious minutes when temperatures remained in the sweet spot for fusion reactions, hot enough to overcome the electromagnetic barrier that keeps positively charged nuclei apart, yet cool enough to prevent the thermal destruction of newly formed nuclear bonds, creating a narrow window of opportunity that would determine the chemical composition of the cosmos for billions of years to come. Research conducted by cosmologists at institutions like Princeton and Cambridge confirms that deuterium served as the crucial bottleneck in cosmic nucleosynthesis, because this fragile nucleus had to survive long enough to participate in subsequent reactions, yet could be easily photodisintegrated by the intense radiation field that filled the early universe, making its formation rate the limiting factor in producing heavier elements. Picture how the universe raced against time during this epoch, with expansion and cooling constantly, reducing temperatures and densities while nuclear reactions fought to build increasingly complex nuclei before conditions became too mild to support fusion processes, creating a cosmic countdown that would determine which elements could form and which would remain impossible until stellar cores learned to recreate these extreme conditions billions of years later. According to theoretical frameworks developed by pioneers like Fred Hoyle and William Fowler, this phase represents the universe's only opportunity to forge light elements through thermal fusion, because stellar nucleosynthesis operates under entirely different conditions that favour the production of carbon, oxygen, iron, and other heavy elements, while being unable to efficiently create deuterium, lithium, and other products of Big Bang fusion. What remains most remarkable about this epoch is how 20 minutes of nuclear activity during the universe's infancy established the chemical foundation for everything that would follow, from the hydrogen fuel that powers stellar cores to the helium that makes balloon flights possible on Earth, forever linking these ancient fusion reactions to every atomic nucleus in your body and every nuclear process powering the stars that illuminate the cosmic stage where consciousness contemplates its own magnificent origins. As we follow that idea deeper into the cosmic alchemy, we witness deuterium nuclei beginning their next chapter of nuclear architecture, as some encountered lone protons to form helium-3, a lightweight isotope carrying 2 protons and 1 neutron, While others collided with fellow deuterium partners to create helium-4, the remarkably stable nucleus that would become the second most abundant element in the universe and remain unchanged for billions of years to come. Picture this extraordinary nuclear choreography where the strong force finally demonstrated its power to overcome electromagnetic repulsion between positively charged protons, binding them together despite their natural tendency to flee from each other, creating the first multi-proton nuclei in cosmic history through pure nuclear determination and quantum tunneling effects. Close your eyes and contemplate the emergence of helium-4 dominance during this epoch, as this particular nuclear combination proved to be the most tightly bound of all light elements, possessing such remarkable stability that it could survive the intense radiation environment of the early universe. While less fortunate, nuclear arrangements quickly disintegrated back into their constituent parts. Take a slow breath as you consider the incredibly narrow temperature window that made this cosmic alchemy possible, lasting only 15 to 20 minutes before the relentless expansion and cooling of space-time shut down nuclear fusion processes forever, creating conditions too mild for the strong force to overcome electromagnetic barriers and bind additional protons into heavier configurations. According to research from nuclear astrophysicists at institutions like Caltech and the University of Chicago, this rapid cooling represented a cosmic race against time, where nuclear reactions fought desperately to build increasingly complex elements, while temperatures and densities plummeted toward values too low to sustain fusion, ensuring that elements heavier than lithium would remain impossible until stellar cores could recreate these extreme conditions billions of years in the future. What captivates scientists most profoundly about this phase is how helium-4 formation proceeded through multiple pathways, with some nuclei emerging directly from deuterium collisions, while others assembled through more complex reaction chains involving tritium and helium-3 intermediates, creating a nuclear web of interconnected processes that maximized helium production during the brief window of opportunity. Imagine the nuclear landscape during these precious minutes when every successful fusion reaction had to compete against photodisintegration, where high-energy photons constantly bombarded newly formed nuclei and threatened to tear them apart before they could participate in subsequent reactions, creating a delicate balance between nuclear construction and destruction that determined the final elemental abundances. Research conducted through precision measurements of primordial element ratios confirms that this epoch established the cosmic helium fraction at approximately 25% by mass, a value that remains virtually unchanged throughout the observable universe and serves as one of the most powerful confirmations of Big Bang cosmology, linking ancient nuclear processes to modern astronomical observations. Picture how the universe's expansion served as both enabler and terminator of this nuclear era, providing the cooling necessary for fusion, while simultaneously ensuring that temperatures would drop below critical thresholds before carbon, oxygen, or other heavy elements could form through triple alpha reactions and more complex nuclear cascades. According to theoretical models developed by cosmologists like George Gamow and Ralph Alpher, this rapid shutdown of primordial nucleosynthesis created the chemical simplicity that characterizes the early universe, leaving behind a cosmos dominated by hydrogen and helium, while reserving the production of heavier elements for the stellar furnaces that would ignite hundreds of millions of years later, forever linking this brief epoch of cosmic fusion to every carbon atom in your DNA, every oxygen molecule you breathe, and every iron nucleus flowing through your bloodstream as a testament to stellar nucleosynthesis that built upon the helium foundation established during these first 20 minutes of nuclear creativity. Now, as we drift deeper into the cosmic inventory established during this remarkable epoch, consider how the universe achieved its primordial abundance pattern that would persist for billions of years, with hydrogen comprising 75% of all atomic nuclei existing primarily as single protons that had survived the great matter-antimatter annihilation, and now stood ready to fuel the first generation of stars that would eventually ignite throughout the cosmic dawn. Picture helium-4 claiming its substantial 24% share of the nuclear census, confirmed by astronomical observations across the observable universe from the most distant quasars to nearby stellar atmospheres, creating a cosmic signature that serves as one of the most compelling pieces of evidence supporting Big Bang cosmology and the thermal history of the early universe. Close your eyes and contemplate the tiny but crucial deuterium fraction at 0.01% of all nuclei, a seemingly insignificant abundance that has become one of the most powerful cosmological indicators available to scientists, because this fragile isotope can only be produced during primordial nucleosynthesis and gets destroyed rather than created in stellar cores, making its observed abundance a direct measurement of cosmic baryon density. Take a slow breath as you consider the trace amounts of lithium-7 scattered throughout the primordial mix at an abundance of 10 to the negative 10th, representing the absolute limit of what Big Bang nucleosynthesis could achieve before cooling and expansion terminated nuclear reactions, leaving behind these rare nuclei as cosmic fossils from the universe's brief career as a fusion reactor. According to research from nuclear astrophysicists at institutions like Harvard and Princeton, beryllium-7 also formed during this epoch but proved too unstable to survive, quickly decaying through electron capture processes that transformed it back into lighter elements, illustrating how nuclear stability played a crucial role in determining which isotopes could persist through cosmic evolution. What captivates cosmologists most profoundly about this abundance pattern is the complete absence of carbon, oxygen, iron, and all other heavy elements that would prove essential for rocky planet formation and biological chemistry, forcing the universe to wait hundreds of millions of years for massive stars to evolve, explode as supernovae, and scatter these crucial building blocks throughout intergalactic space. Imagine the chemical simplicity that characterized the post-nucleosynthesis universe, where only the lightest elements existed in significant quantities while the entire periodic table beyond lithium remained locked away in potential, waiting for stellar nucleosynthesis to unlock the nuclear pathways leading to atomic diversity and molecular complexity. Research conducted through cosmic microwave background observations by satellites like Planck and WMAP has confirmed these primordial ratios with extraordinary precision, measuring the acoustic oscillations in the early universe that reflect the exact baryon-to-photon ratio needed to produce the observed elemental abundances through thermal nuclear reactions. Picture how this chemical inventory would seed the formation of Population 3 stars, the first stellar giants that contained virtually no heavy elements, and burned with such intensity that they lived fast, died young, and enriched the cosmos with freshly forged carbon, oxygen, and silicon through their spectacular supernova explosions. According to theoretical models developed by pioneers like George Gamow and Fred Hoyle, these abundance ratios represent a cosmic fingerprint that connects modern astronomical observations to nuclear processes that occurred during the universe's first 20 minutes, linking every helium atom in party balloons to ancient fusion reactions, every deuterium nucleus in heavy water to primordial nucleosynthesis, and every lithium ion in modern batteries to the cosmic alchemy that established the chemical foundation for all subsequent cosmic evolution, stellar formation, and the eventual emergence of planetary systems capable of supporting the complex chemistry that makes consciousness possible in this vast and magnificent universe. What happens when the universe is too bright to see through? Tonight we enter the longest chapter in the pre-atomic story, spanning nearly 400,000 years when the cosmos existed as a blazing hot plasma where electrons, protons, and photons danced together in an intimate cosmic waltz that made transparency impossible, creating conditions where light could travel no farther than a few centimeters before colliding with free electrons and scattering in random directions like headlights struggling through impenetrable fog. Picture this extraordinary state where Thomson scattering dominated the cosmic landscape as every photon that tried to journey across space immediately encountered wandering electrons that deflected these light particles along chaotic paths, ensuring that no electromagnetic radiation could propagate freely through the universe and making the entire cosmos glow with trapped energy that had nowhere to escape. Close your eyes and contemplate this opaque realm where photons remained prisoners of the electron sea, bouncing endlessly between charged particles in a cosmic pinball machine that prevented any form of electromagnetic observation, creating conditions where the universe blazed with internal light yet remained completely invisible to any hypothetical observer trying to peer across cosmic distances. Take a slow breath as you consider how temperatures during this epoch slowly declined from tens of thousands of Kelvin down to roughly 3,000 Kelvin over the course of nearly 400 millennia, cooling at a rate determined by cosmic expansion, yet remaining far too hot for electrons to settle into stable orbits around atomic nuclei, maintaining the ionized conditions that kept the universe opaque to electromagnetic radiation. According to research from cosmologists at institutions like Princeton and Cambridge, this extended period represents the universe's adolescence, when nuclear fusion had ended but atomic formation remained impossible. leaving behind a cosmic medium filled with ionized gas where every proton existed as a naked nucleus, desperately seeking electrons that possess too much kinetic energy to be captured and bound. What captivates astrophysicists most profoundly about this phase is how the cosmic soup maintained perfect thermal equilibrium between matter and radiation, with photons constantly exchanging energy with electrons and protons through electromagnetic interactions, creating conditions where temperature remained uniform throughout the observable universe, despite its continued expansion and gradual cooling. Imagine the cosmic environment during these millennia when no atoms existed anywhere in space, only bare nuclei and free electrons swimming through an ocean of photons, creating a fundamentally different kind of matter than anything we observe in our modern universe, where atomic structure provides the foundation for chemistry, biology, and all forms of complex organization. Research conducted through cosmic microwave background observations reveals that this plasma era established the acoustic oscillations that we can still detect today as temperature variations in the ancient radiation, showing how sound waves propagated through the cosmic medium when photons and electrons remained coupled through electromagnetic forces, creating pressure waves that would eventually influence galaxy formation billions of years later. Picture how this epoch represents the universe's final act of perfect democracy, where every region of space maintained identical physical conditions and no structure could form because electromagnetic radiation pressure prevented gravitational collapse, ensuring that matter remained smoothly distributed, while dark matter began its invisible work of creating gravitational wells that would later trap ordinary particles once atoms finally learned to exist. According to theoretical models developed by cosmic evolution specialists, this era set the stage for everything that would follow by gradually cooling the universe toward the critical temperature where electron capture could occur, while simultaneously allowing dark matter to begin clustering into the cosmic web that would provide scaffolding for galaxy formation once electromagnetic forces released their grip on cosmic structure and allowed complexity to emerge from primordial simplicity. As we follow that idea deeper into this cosmic symphony, we witness the emergence of acoustic oscillations rippling through the primordial plasma-like sound wave as propagating through a medium denser and more responsive than any terrestrial substance, creating pressure variations that would echo across cosmic time and eventually determine where galaxies would form, billions of years after these ancient vibrations first disturbed the cosmic calm. Picture these magnificent pressure waves arising from the eternal struggle between radiation forces trying to smooth out density fluctuations and gravitational attraction attempting to amplify them, creating a cosmic tug-of-war where photon pressure fought against matter's tendency to clump together, generating oscillations that propagated at precisely 1/3 the speed of light through the coupled photon-baryon fluid. Close your eyes and contemplate how these baryon acoustic oscillations establish the fundamental scale that would govern large-scale cosmic architecture, imprinting a preferred separation distance of about 500 million light-years that we can still observe today in the clustering patterns of galaxy superclusters, creating a cosmic fingerprint that connects modern astronomical surveys to sound waves that propagated through the universe when it was less than 1% of its current age. Take a slow breath as you consider how dark matter began its crucial work during this epoch, forming the invisible gravitational scaffolding that would eventually trap ordinary matter once atoms learned to exist. Because unlike photons and electrons, dark matter particles felt no electromagnetic pressure and could respond purely to gravitational forces, allowing them to start building the cosmic web while visible matter remained trapped in the plasma dance. According to groundbreaking observations from satellites like BioMap and Planck, these ancient sound waves left permanent imprints in the cosmic microwave background radiation that we can detect and analyze with extraordinary precision today, revealing the exact conditions that existed in the primordial plasma, and confirming theoretical predictions about how matter and energy behaved during this critical epoch of cosmic evolution. What captivates cosmologists most profoundly about this phase is how photon pressure served as a cosmic regulator that prevented significant clumping of ordinary matter, ensuring that the universe maintained remarkable homogeneity on large scales while allowing tiny density fluctuations to persist and grow through gravitational amplification once electromagnetic coupling finally ended and atoms could form stable structures. Imagine the cosmic landscape during these millennia, when every attempt by matter to collect into denser configurations was immediately opposed by radiation pressure pushing back against gravitational collapse, creating an equilibrium where structure formation remained frozen in. Potential while dark matter worked invisibly to prepare the gravitational wells that would become galaxy clusters and cosmic filaments. Research conducted through precision measurements of cosmic microwave background anisotropies confirms that these acoustic oscillations created a series of peaks in the temperature power spectrum that encode detailed information about cosmic geometry, matter, density, and the fundamental parameters governing cosmic expansion, transforming ancient sound waves into one of our most powerful tools for understanding the universe's composition and evolution. Picture how these pressure waves established the cosmic distance scale that would later influence everything from galaxy formation to the distribution of dark matter halos, creating correlations between widely separated regions that persist today as the baryon acoustic oscillation signal that astronomers use to measure cosmic expansion and probe the nature of dark energy driving current cosmic acceleration. According to theoretical frameworks developed by cosmic structure formation specialists, this radiation matter dance represents the universe's final period of perfect coupling between electromagnetic forces and gravitational effects, creating conditions where quantum fluctuations from inflation could grow into classical density perturbations, while maintaining the precise relationships needed for complexity and life to eventually emerge from cosmic simplicity. Now, as we drift deeper into this cosmic waiting period, consider the extraordinary patience required for nearly 400,000 years of gradual cooling, as the universe slowly transformed from a blazing inferno of 10,000 Kelvin down to the critical threshold of 3,000 Kelvin, where electrons would finally possess calm enough to be captured by atomic nuclei and begin the age of neutral matter that would change everything about cosmic evolution. Picture this epic span of time that dwarfs all of recorded human history, during which temperatures declined with glacial slowness as cosmic expansion stretched and diluted the primordial energy, creating conditions where thermal motion gradually weakened its grip on charged particles while gravitational forces patiently waited for their opportunity to begin sculpting cosmic architecture. Close your eyes and contemplate the pivotal moment around 50,000 years after the Big Bang, when matter-radiation equality occurred, marking the transition from a universe dominated by photons to one where massive particles finally claimed control over cosmic dynamics, shifting the balance of power and enabling gravitational collapse to begin competing effectively against electromagnetic pressure for the first time in cosmic history. Take a slow breath as you consider how dark matter enjoyed a crucial advantage during this epoch because it remained completely immune to photon pressure, allowing these invisible particles to respond purely to gravitational attraction while ordinary matter remained trapped in its electromagnetic dance with radiation, creating the cosmic irony where the mysterious dark component began building structure before visible matter could even form stable atoms. According to research from cosmologists at institutions like Harvard and Princeton, gravitational seeds established during cosmic inflation began their slow amplification during this phase, with tiny density fluctuations growing imperceptibly through gravitational attraction, while electromagnetic forces prevented any dramatic clustering, creating the delicate balance needed to eventually produce the cosmic web of galaxies without allowing a premature collapse into black holes. What captivates astrophysicists most profoundly about this waiting period is how dark matter, particles carved out invisible gravitational wells that would eventually become galaxy clusters and cosmic filaments, working like cosmic sculptors to prepare the architectural framework that ordinary matter would inherit once atoms finally learned to exist and electromagnetic coupling released its grip on cosmic structure formation. Imagine the cosmic landscape during these millennia, when patience became the supreme cosmic virtue as fundamental forces prepared for their next great collaboration, while expansion continued its relentless work of cooling and diluting the primordial medium, creating conditions where the most important transformations in cosmic history would soon become energetically favorable. Research conducted through cosmic microwave background observations and large-scale structure surveys confirms that this epoch established the foundation for everything we observe today, from the largest cosmic voids to the densest galaxy clusters, all stemming from the careful preparation that occurred during these seemingly uneventful millennia, when the universe appeared static, yet worked invisibly to set the stage for atomic formation. Picture how this extended cooling period represents cosmic anticipation on the grandest scale, where every Kelvin of temperature decrease brought the universe closer to the critical threshold where electrons could finally be tamed by electromagnetic attraction, protons could capture their electronic partners, and neutral hydrogen would emerge to begin the next chapter of cosmic evolution that would eventually lead to star formation, galaxy assembly, and the emergence of complexity from primordial simplicity. According to theoretical frameworks developed by cosmic evolution specialists, this long wait exemplifies how the universe operates according to principles where patience and gradual change enable the most profound transformations, setting the perfect stage for recombination through hundreds of thousands of years of careful preparation that would culminate in one of the most important phase transitions in cosmic history. How did the universe finally learn to let light travel free? Tonight we witness the most transformative moment since the Big Bang itself, as cosmic temperatures finally drop to the critical threshold of approximately 3000 Kelvin, cool enough for electromagnetic attraction to overcome thermal motion and allow protons to capture wandering electrons for the first time, ending nearly 400,000 years of ionized chaos and beginning the age of neutral matter that would revolutionize cosmic evolution forever. Picture this extraordinary epoch when electron capture became possible as atomic nuclei finally gained the power to hold on to their electronic partners, creating the first stable hydrogen atoms where negatively charged electrons settled into quantum orbits around positively charged protons, forming the fundamental building blocks of chemistry and establishing the foundation for all molecular complexity that would eventually emerge. Close your eyes and contemplate how neutral hydrogen emerged as the universe's first genuine atomic species, followed closely by helium atoms that also learned to capture their full complement of electrons, creating a cosmic transformation from a sea of naked nuclei and free charges into a realm of electrically balanced atomic structures that could interact through entirely new electromagnetic mechanisms. Take a slow breath as you consider how this atomic formation marked the end of ionization throughout the observable universe. Removing virtually all free electrons from cosmic space and eliminating the Thomson scattering that had kept photons trapped since nucleosynthesis ended, creating conditions where electromagnetic radiation could finally propagate across vast distances without obstruction for the first time in cosmic history. According to research from atomic physicists at institutions like MIT and Caltech, this recombination process involved intricate quantum mechanical pathways known as two-photon transitions, where electrons cascaded down through energy levels while emitting multiple photons to avoid producing ultraviolet radiation energetic enough to immediately reionize the newly formed atoms, ensuring that atomic formation could proceed efficiently despite the intense radiation environment. What captivates cosmologists most profoundly about this phase is how the universe achieved transparency through such delicate quantum processes, requiring electrons to navigate complex energy landscapes while avoiding the production of ionizing photons, demonstrating how atomic physics and cosmic evolution became intimately connected through the fundamental laws governing electromagnetic interactions between charged particles. Imagine the cosmic moment when the last free electrons found their atomic homes, ending the era of opacity and beginning the epoch of transparency, allowing photons that had been trapped since the first 20 minutes after the Big Bang to finally escape their electromagnetic prison and begin journeys that would eventually carry them across billions of light years to reach telescopes and eyes that would not exist for billions of years. Research conducted through precision spectroscopy and cosmic microwave background observations confirms that this atomic formation occurred rapidly and completely, transforming the universe from opaque plasma to transparent gas in a relatively brief period, creating the sharp boundary between the visible cosmic surface and the invisible earlier epochs that remain forever hidden behind the veil of recombination. Picture how this transformation enabled the first chapter of cosmic structure formation, as neutral atoms could finally respond to gravitational attraction without being disrupted by photon pressure, allowing matter to fall into the dark matter wells that had been waiting patiently for hundreds of thousands of years to capture their first ordinary particles and begin building the cosmic architecture that would eventually host galaxies, stars, planets, and conscious observers contemplating their own atomic origins in the vast cosmic theatre. As we follow that idea deeper into this cosmic dawn, we witness photon decoupling occurring for the first time in universal history, as electromagnetic radiation finally gained the freedom to travel unimpeded across vast distances, no longer constantly colliding with free electrons but streaming through space in straight lines that would carry ancient information across billions of years to future observers equipped with telescopes sensitive enough to capture these primordial messengers. Picture this extraordinary moment when the universe became transparent as the cosmic fog lifted, transforming from an opaque medium where light could travel mere centimeters before scattering to a clear realm where photons could journey across galactic distances without obstruction, creating the conditions that would eventually enable astronomy, vision, and all forms of electromagnetic observation. Close your eyes and contemplate the last scattering surface that formed during this epoch, representing the furthest boundary that any electromagnetic observation can penetrate into cosmic history, creating a spherical shell around us that marks the moment when photons last interacted with matter and began their epic journeys through expanding space-time toward distant futures they could never anticipate. Take a slow breath as you consider how these ancient photons constitute the cosmic microwave background radiation that fills the universe today, carrying within their wavelengths and polarization patterns the detailed fingerprints of physical conditions that existed when the cosmos was only 380,000 years old, providing our most direct observational connection to the primordial universe and its fundamental properties. According to measurements from the Planck satellite and other precision instruments, these photons have cooled from their original temperature of roughly 3000 Kelvin down to just 2.73 Kelvin after 13.8 billion years of cosmic expansion, their wavelength stretched by the growth of spacetime itself from visible orange light into microwave radiation that requires specialized detectors to observe and analyze. What captivates cosmologists most profoundly about this electromagnetic liberation is how it created the observable universe as we know it, establishing the boundary between the visible cosmos that astronomy can study and the hidden epochs that remain forever sealed behind the wall of opacity that characterized the pre-recombination era, making these ancient photons our oldest possible source of direct information about cosmic conditions. Imagine the significance of Planck satellite data that maps this ancient radiation in exquisite detail, revealing temperature fluctuations of just millionths of a degree that encode information about dark matter, density, cosmic geometry, the seeds of galaxy formation, and the fundamental parameters governing cosmic expansion, transforming these primordial photons into one of our most powerful tools for understanding the universe's composition and evolution. Research conducted through cosmic microwave background analysis confirms that this moment of photon release marked not just the birth of cosmic transparency, but also the beginning of structure formation on all scales, as matter could finally fall into gravitational wells without electromagnetic interference, initiating the long process that would eventually lead to star formation, galaxy assembly, and the emergence of planetary systems capable of supporting the complex chemistry that enables consciousness to contemplate its own cosmic origins. Picture how every photon released during recombination carries within its properties a unique record of the density, temperature, and velocity conditions at its point of origin, creating a cosmic library where each microwave wavelength tells a story about the primordial universe and its transition from chaos to the ordered structures that would eventually give rise to everything from spiral galaxies to the biological processes that power the neural networks contemplating these magnificent cosmic transformations in moments like this one. Now, as we drift deeper into this cosmic epilogue, consider how the Dark Ages began immediately after recombination ended, plunging the universe into a period of profound darkness where no stars had yet learned to ignite, and the only electromagnetic radiation came from the faint 21-centimeter emissions of neutral hydrogen atoms, creating a cosmos illuminated solely by the afterglow of creation and the whispered radio signals of atomic transitions that would persist for hundreds of millions of years. Picture this extraordinary epoch when gravitational growth finally gained supremacy over all competing forces, allowing dark matter halos to form and amplify their invisible architecture, while ordinary matter remained passive, waiting for gravitational attraction to guide it toward the cosmic scaffolding that had been growing steadily since matter-radiation equality established dark matter's advantage over photon-coupled particles. Close your eyes and contemplate how baryon infill began during this phase, as neutral hydrogen and helium atoms responded purely to gravitational forces for the first time in cosmic history, streaming toward the densest regions of dark matter, concentration, and beginning the process of gas accretion that would eventually provide the raw material for stellar nurseries and galactic formation throughout the observable universe. Take a slow breath as you consider how structure formation accelerated during these dark millennia, with tiny density fluctuations that had been frozen during the plasma era finally gaining the freedom to grow through gravitational amplification, creating hierarchical clustering where smaller dark matter halos merged to form increasingly massive structures that would eventually become the sites of galaxy formation and stellar birth. According to research from cosmologists at institutions like Princeton and Harvard, this epoch represents the universe setting its cosmic stage for everything that would follow, establishing the gravitational wells that would trap gas, compress it to stellar densities, and ignite the nuclear furnaces that would illuminate the cosmos and begin the synthesis of heavy elements essential for planetary formation and biological complexity. What captivates astrophysicists most profoundly about this dark period is how invisible processes during these apparently empty millennia established the fundamental architecture of cosmic structure, creating the cosmic web of dark matter, filaments that connects galaxy clusters across billions of light years, while carving out vast cosmic voids where very little matter would ever accumulate. Imagine the cosmic landscape during these silent years when gravity worked patiently to organize matter according to the density patterns established during inflation and preserved through recombination, building the foundations for everything from dwarf galaxies to massive elliptical systems, while ordinary matter gradually learned to follow the invisible roadmap that dark matter had constructed. Research conducted through large-scale structure surveys and computer simulations confirms that this epoch transformed tiny primordial fluctuations into the pronounced density contrasts needed for gas collapse and star formation, amplifying cosmic architecture through pure gravitational dynamics while maintaining the precise relationships between structure and scale that would eventually enable the formation of stable stellar systems and planetary environments. Picture how this Dark Age conclusion represents not an ending, but a cosmic preparation, where hundreds of millions of years of patient gravitational work created the conditions needed for the first stars to ignite, the first heavy elements to form, and the first steps toward the chemical complexity that would eventually enable molecules, planets, atmospheres, and the intricate biological processes that allow consciousness to emerge and contemplate the magnificent cosmic journey from quantum foam to atomic matter to the vast universe of stars and galaxies that surrounds us today. Tonight, as you breathe slowly and feel your heartbeat marking time in this ancient cosmic rhythm, remember that every atom in your body carries the memory of these extraordinary transformations, forged in the primordial fire when quarks learned to dance together, when nuclei discovered how to capture wandering electrons, when the universe finally became transparent and allowed starlight to begin its billion-year journey to your eyes. Take a moment to contemplate how you are literally made of stardust that began as quantum foam, evolved through plasma and nuclear fire, survived the great matter-antimatter annihilation, and emerged from the cosmic dark ages as the raw material for conscious thought contemplating its own magnificent origins across nearly 14 billion years of cosmic evolution. Close your eyes and feel yourself connected to this vast story that stretches from the unknowable singularity through inflation and nuclear fusion to the moment when atoms first formed and light learned to travel free, linking your existence to every major transformation in cosmic history and making you a living embodiment of the universe's journey from simplicity to complexity, from chaos to consciousness, from quantum uncertainty to the ordered beauty of galaxies, stars, planets, and minds, capable of understanding their own cosmic heritage. If you're kind enough, a gentle like or a quiet tap on subscribe would mean the universe to me, helping these cosmic stories reach other curious souls who wonder about their place in this magnificent dance of matter and energy that began before atoms had names and continues today in every breath you take, every thought you think, every moment you spend marveling at the extraordinary fact that the cosmos became aware of itself through the emergence of consciousness from the same primordial ingredients that once swam freely in that ancient sea of quarks and gluons. Share with us in the comments where you are listening from tonight and what time the cosmic microwave background radiation is whispering its ancient secrets to your corner of this vast universe, because your presence here, your curiosity, your willingness to contemplate these deep mysteries represents the universe's greatest achievement, the emergence of minds capable of understanding their own cosmic story and finding wonder in the magnificent journey from the first moment after creation to this present instant when consciousness meets cosmos in the eternal dance of existence contemplating itself across space and time.